Tady stream už běží. Už tam je něco. Je tomu rozumět? Je něco slyšet? Není slyšet? Aha, počkej, tak já ještě něco zkusím. Nemá to zpoždění? Let me start? Yeah. Tak, dobrý den, my bychom vám chtěli popřát hezké dopoledne a říci vám něco o vestavěné umělé inteligenci. Dneska určitě víte, že je řada systémů, které využívají AI, jsou řízený daty a těmi věcmi. No a ty systémy se pořád stávají složitějšími, jak se v tom pomalu ty programátoři nevyznají a vlastně jakmile ty systémy chodí velké množství dat a zase ty další systémy to zpracovávají, tak potom vytváří nějakou zpětnou vazbu, která potom vlastně tohleto všechno řídí a vytváří z toho nějaký funkční ekosystém. A kolega Albert, kterého tady vítám, so let me to introduce my colleague Albert, who is coming from University of Krems, and he will tell us some interesting information regarding the embedded intelligence. So Albert, it's yours, and go on, please.
Okay. Thank you for the introduction. Dobrý den. That's the only two Czech words I know. Maybe I know two more, but I'm not sure. So please turn off your mobile if you haven't done it, or put it to silent mode, flight mode. I always put it here for myself because I also regularly forget about this. So, welcome to my presentation. Today I want to draw a very big arch from embedded systems over the Internet of Things to what is called embedded intelligence. But we will come to this in the lecture given here. Hansa was so nice to introduce me, so I think you said everything here. So the only thing I want to stress out, I'm a nice person. Since you will not have an exam here, my gift to you will also not be good, because I tell all of my students, if you find a mistake in my presentation, you get 1 extra point on your exam. So bad luck for you, but nevertheless, I think we will have a lot of fun here, and I hope that there is interesting information for you in this presentation. So let's start into the topic. What is our life all about? There's multiple answers, but technology is seen. Our society is at the moment at the brink to be data-driven. So data is what we need, what is here. I hope I will not destroy technology, but then I can see a little bit here. So it starts, that's the domains where I'm working, that's the 3-4. So I'm in industrial automation, industry 4.0. Data is of utmost importance. Without this, it will not work. We have smart cities, maybe not that far as industry is at the important thing, and that's why I'm doing most of my research, is the energy transmission. Here data is required to coordinate renewable production of energy, which is not stable as a power plant, which you cannot say, turn a switch on and say, now I have electricity. When the wind blows, then electricity is here. When it's not blowing, it's not here. So here a lot of communication is needed, a lot of data is needed to coordinate that we all have the right amount of energy when we need it, or that we change our expectation that we say, okay, I will do the energy-intensive things at midday, when the sun is shining, when the wind is here. Also, the Green Deal from the European Union focus on this. It set a real focus on the Green Deal data space. Yeah? They identified that without data, we will not achieve what our society needs and wants to achieve at the moment. And everything is called digitalization. Yeah? So that's what then the business term from managers is, we need to digitalize it. So let's see. So if I look at our administration at our university, a lot of public authorities in Austria, digitalization often for them stops when, oh, I have a web form where you can put in the data manually. No, that's not digitalization. Digitalization means data is generated automatically, because then I can get the data in the right amount. Yeah? But this will also mean I need to have a lot of sensors, a lot of devices gathering this data. And 4 years ago approximately, somebody from industry framed the word the trillion sensor hype. So they forecasted, here's a figure from 2023, but it was a few years earlier. They forecasted that we will have in 4 or 5 years trillions of sensors around the world. Yeah? And that's something you can already see on your mobile phone. I ask you to turn off. Yeah? There's at least 10 sensors even in the cheapest mobile phone. In more advanced and expensive ones, there are more sensors. In the car and so on, we come to this at a later point. Yeah? And the important thing is now, it's not just enough to sense data. You need to transmit it, to process it. So that's the important thing. Sensors and sensor systems, they distribute, they transform in something which is really intelligent, which becomes systems of systems. Yeah? And in the end, it's the Internet of Things. That's the next buzzword which is around. I will try a little bit to demystify this. Yeah? But this Internet of Things will then connect all of these devices to transfer this generated data to make it possible that applications is using it. So I told you there are 10 sensors minimum in a mobile phone. I can also list it for a car, for a factory. The power of 10 increases by each of them. But to give you an idea of how many data are in the world, and at the moment, okay, here it is. We just see the top of the iceberg of data. So what is here, that's, let's say, very good estimations, but they are still not showing what the total amount of data is. Yeah? And if you look at the smart connected home, yeah? So single flat, single house with some home automation, already in this house, you generate 142 megabytes of data a day. And it's without video, without your kids watching Netflix, Disney Plus, Prime, and so on. So that's pure automation data, like opening windows, like the data in your heating system, which is exchanged, what your dishwasher is doing, what your fridge is doing, and so on. Yeah? If we going a little bit more to a factory, and it's not a big one, it's not a gigafactory, it's a typical small, medium-sized factory. This factory is already producing 1 terabyte of data, yeah? Which is 3 magnitudes above. And if you go up to, let's say, other applications like our which is going towards automatic driving, so a car, which is typical today, this car, and cars are at most of the time not used, yeah? You're not driving 24 hours. But this car is producing 4 terabytes of data, which includes video data, I must admit, in the car. Yeah? So if you have an entertainment system, you're, let's say, on the top of the 4 terabyte. If you don't use an entertainment system, maybe you will be at the half of it. Yeah? So we can go to an aircraft, which is let's say in the magnitude of a car, so it's 20 terabytes, and somebody or some organization made the effort to calculate how many data is in the internet on a day, and they are coming to 2.5 petabytes, which is 10 to the power of 15. Yeah? This includes also video data, and video data you can always, and the rule of thumb is today half of the amount of data. Yeah? So what does these figures show you and tell us as scientists? Yeah? It's data processing is needed. Yeah? You cannot scan 2.5 petabytes manually. Yeah? So there needs to be some aggregation. And that's a very important thing which I want to stress. Yeah? Today the problem is in data is on the one hand to have enough, for example, to train artificial intelligence, but the most important thing for the application is to reduce this data that you get the necessary amount you need for your decisions in your application. And this reduction is really important. Yeah? The next important thing about this, yeah, it's maybe at a car you can say, everything is one place, a car is one system. Yeah? But this data, even in a car, is distributed. There will be some data in the braking system, some in the engine control system, some in the home, in the car entertainment system. So this distributed data need also to be connected and exchanged. Yeah? So you need to also process it, and in the end, all this processing will influence data quality. Yeah? So keep this a little bit in mind, that this is also an important thing. So I want to now take a step back. We have been now at a very high height of fly and look down at these petabytes of data. So what are now the players in our universe which sense the data, which process this data? So, yeah, let's look at ourselves. It's not a bionic approach, I must admit, but I like the pictures, and I think they make it very memorable what an embedded system is. It's like in the Kung Fu series where some master shows you, this is on the back side is the picture of the human, on the front side the earth, and then you understand the earth if you understand the human. Yeah. So what does an embedded system have? It's like almost like us. What do we have? If there is a surface, we touch it with our fingers. So we have receptors, we have nerves. This girl maybe didn't touch this nice surface, maybe it touched a hot surface. Yeah. Then we have memory and computing power. So we have our brain. And the most important thing, even with us, and look at this girl, yeah, or I experienced it with my son too, yeah, it depends also on the interaction and communication, how we interpret data. Yeah. If I touch a hot surface as a boy, and my mother said, "Oh God, you touched it," then I will cry double the intensity because I get the feedback that's something bad. Yeah. If my brother said, "Oh, uncool, you cried, that's not so hot," yeah, then I will say, and we'll say, "No, that's not so hot." Yeah. So, but let's go a little bit back to technology. But keep this picture in mind. I think maybe it will help. Yeah. So let's start with the touching, with the fingers. So what is a sensor? Yeah. And I think make yourself aware about these simple functions so that you're able to really identify what is the sensing part in the system. Yeah? A sensor is, on the one hand, a device which measures a physical quantity, roughness here, temperature, for example, of this surface. Yeah? The second aspect the sensor has, it transfers this physical quantity into another quantity, mostly electricity. Yeah, that's the third part. So 2 and 3 are almost the same in today's sensors. In many old sensors, but also in some other sensors, there are intermediate physical quantities, but in generally it's 2 and 3 are the same because we are interested in electrical signals because this is what we can process with our systems. Yeah? So, yeah, you might know some of them. So this is a microphone, for example. This is a pressure sensor, a humidity sensor. This sensor is maybe, since we're here at the Faculty of Agriculture, also interesting. It's for soil moisture. And this sensor here, it's from my university, from the museum part. It's an ohm meter, so it measures the electrical resistance. And here, this is one of the rare sensors which don't produce an electrical signal. It produces a mechanical signal, an elongation or a twisting of this gauge. Yeah, so that's a sensor. Remember, we transfer a physical quantity into an electrical signal. Then you have an embedded system, and the next 5 minutes you will be bored by definitions. So, an embedded system is a computer system which does a particular task inside a machine or a larger electrical system. So, embedded means in a machine, yeah? In this presenter, in the mobile phone, in the microphone, wherever it is. Yeah? So, important thing, it's a computer, so it's memory, it has a processor, and it has input-outputs to sensors, to some peripheral devices. Important thing in this definition, it's very machine-centric. So the network option is not really mandatory. So your washing machine today typically don't have an internet plug, yeah? But it has an embedded system to control the motor, the introduction of the cleaning fluid, and so on. Yeah? So then there was around the 1990s, scientists like me, we have been bored, or actually we not have been bored, but everybody knows embedded systems, so we have to invent something new. And you will see it maybe also in your science when you work longer there. Then somebody called it a cyber-physical system. So what is a cyber-physical system? Yeah? They introduced two main things. Yeah? They introduced that it's collaborating, so they added the network to the embedded system, and they set a big focus that you interact with the physical environment. Yeah? So that's the very important two things. Yeah? And I want to stress the physical environment. That's why it's called cyber-physical, connection of the IT and the physical world. Yeah? So that's the next step of this evolution, which is still an embedded system. So this definition is like surrounding spheres. And then, yeah, we from the sensor part, we thought, okay, cyber-physical, that's too fancy for us. We want to have it more structured for sensors, and that's what we are interested in, or what my department is interested in. We try to structure it in a better way, in a more modular way. Yeah. So we identified in such a sensor system, which is, let's say, subordinate to the cyber-physical system, we identified 4 main blocks which are in there and which are important, and which, if you want to make a sensor, all needs to be covered. Yeah? Is that you have a measuring unit, that's the actual sensor, transfer the physical thing to an electrical signal. Then you have a lot of electronics inside, because typically today this electrical signal is really ugly, to say it in a yucky or whatever you want to call it. It's noisy, it has outliers, whatever. So you need to condition this, yeah, so to filter outliers and so on. Yeah. And then most of the sensors, then it's not done. Yeah, a video camera is also a sensor. You can have the best picture of the video camera, but still don't know from a computer point of view what is on the picture. Yeah? So you need software, you need intelligence. Yeah? And then finally, like with the cyber-physical systems, you need the communication. So you need to integrate it in your system, because the best sensor The best hand will not work if it's chopped off here and your brain don't know what happens here. Yeah. So, and then finally, or not finally, it was before the integrated sensor systems. It's also around the 1990s this trend started to take off, was the Internet of Things. And there people want to connect everyday objects with the internet. So the idea was everything has an IP address. That's to be a little bit exaggerated, but that was the marketing talk about this. And we have three main properties. They say every everyday object is an embedded system or a cyber-physical system, so it has sensing, networking, and processing capabilities. It communicates. So you might now say, oh, that's a cyber-physical system. Why do they call it Internet of Things? Because it communicates over the internet. Yeah? And today, I think we are quite close to this. Also, in my personal opinion, we will never reach the fact that every sensor has an IP address. This technical, in my opinion, doesn't make sense. Yeah? So we might have hierarchical networks, but in the end, today we are going that we put all data, or at least the reduced data, so important data, to some cloud space, to the internet. Yeah? Doesn't matter whether this is at Amazon or locally at your premises, that's details. Yeah? But I think that's where we are going today in our system design. So I titled this slide a little bit juicier. So here you have a nice picture of the Internet of Things, taken from free pics, so it's more for the marketing. So it says everything is connected. What should we say? Should this figure say and intuitively say? Yeah, is the Internet of Things at the moment connects rather big devices, yeah, like a camera, like a TV, like a dishwasher. It doesn't connect at the moment these really small things. Yeah. It's cloud-centric. I mentioned this before. Yeah. And the important thing I didn't forget to mention before is Internet of Things. The humans are excluded. Yeah. So it's a pure machine-to-machine communication. Good. So you should know what an embedded system is, a sensor, and what the Internet of Things is now. So let's have a little bit more look into what is an IoT system. I think that's also important. I don't know how many of you have a technological background, so I will try to fly somewhere beneath the clouds. If I'm too high, then please raise your hands. Then I will try to fly deeper. But you know, I'm not a combat pilot. I will not fly 2 meters above the ground. Yeah, it's too dangerous for me. So let's see. But I think I will meet it. Yeah. Good. So we have this device. That's an IoT device. We have whatever I mentioned before. We have the microcontroller inside here. We have the communication device. We have the sensor. We have actuators. What additionally is in such an IoT device today, and what is important to remember beyond the definition I made before? Yeah? It's these two things. Yeah? That's really, energy is really, really important in IoT devices, because you don't want to change a battery. Many systems are not connected to the power grid. They are not on a power plug. Yeah? They work mobile. Some, temperature sensors. You don't want to put kilometers or meters of cable to connect this temperature sensor in your flat. Yeah? You want to put it somewhere. Yeah. Stick it here to the wall. Screw it somewhere. Yeah. And therefore energy is really, really important. And since batteries don't last for long, you will also think about energy harvesting. So if I touch this board, maybe we can harvest then from the movement of the board the necessary energy. Yeah. So this is two additional things which we have to consider. But nevertheless, what I told you before, everything is true. We are having a sensor, we take data, we transmit it. So that's our IoT device in the bottom. Yeah? And now the IoT system starts. So we need to flip. Here are the sensors, the devices. Yeah? So the sensors, and that's maybe I need to stress this a little bit. If you look at the system today, focus will be a data collection. But the Internet of Things is more than just collecting. So you often, if you look at brochures of manufacturer, you might get the impression, oh, I'm just collecting data. But the interesting thing is actually to do an action. Yeah? But both are important on the device side. Yeah? Then, since these devices are very small, must not consume a lot of energy. Yeah? Typically, these devices connect with a dedicated communication protocol, mostly a radio protocol, so wireless, to something which is called a gateway. In the IoT naming, this gateway is in the connectivity layer. Yeah? So here you connect your sensors to the cloud, to the internet. That's a very, very important layer in most IoT systems, because here you have to translate from low power, low resource, low computational capability devices to something in the internet where, my smartphone today has 100 times the computation power of the first computer I used in my life. So this was when I was, I think, 13 years old. My father bought a computer for his company. Yeah? He would be surprised at this time if he would have a smartphone. This would have filled this room, such a computer, and costs millions of euros at this time. Yeah? But you see, it's a huge difference, in the capabilities. Here, I just interpret a single temperature signal. Here, I'm doing AI, video processing, whatever. Yeah? So then let's go to the third layer of the Internet of Things. Most IoT system, or actually all that I know, have in this cloud layer, they have two main functions. Yeah? They have what I called here the cloud layer itself. Yeah? This is mostly a storage and management layer. So if you look at the picture, you have the databases here. That's the first functionality of stored or located in the cloud, And then you have a second layer in the cloud, which is the analytics or application layer, which is doing data processing. So, for example, if I have here, let's say, multiple temperature sensors from different rooms, assume room 1 is red, room 2 is yellow, and the other room is green. Then this processing might calculate the mean temperature of the whole house. Yeah? So this is a simple one. It could also be an AI program which is doing things here. And the second thing of this analytics and application layer is the provisioning of data. Yeah? I will spend at the end of my presentation a more intensive part of it, but think about the internet and the web server there. How many people are connecting a web server to retrieve some data? If you ask a very simple sensor, please answer 100,000 requests within a minute, no sensor will be able to do it. It maybe has a 5 kilobit per second connection, even lower, and low processing capabilities. So here we have again two different magnitudes of the frequency data are needed. In the internet, The frequency is very high. We have very high number of people who want to retrieve data. On the sensor, it's very low. So that's the important thing on the data provision. And then many, or most, all IoT systems, at some point they have a connection to us, because they don't live for themselves. So there is often a visualization layer and a personalization added to this. So 5 layers of an IoT systems: sensors, connectivity, the data and storage, the analytics, and the user interface. One might wonder why we don't have the Internet of Things already for 30 years and it's already perfectly working. The Internet of Things needs certain enablers, and they just reached the maturity in the recent years, and will continue to be more mature. It's what we need is cheap sensor technologies, especially low power sensor technologies. This is really a hard part for us electrical engineers. We have to have low power in all aspects, so we need to have low power electronics to reach the mobility, to reach this integration. We need to have good connectivity, and not only on the IP layer, but especially on these communication protocols, the low power wide area networks, for example, 5G, narrowband IoT, Bluetooth, whatever, who can connect very small devices which just want to transmit very, very small amounts of data. Cloud computing, at the moment, it's maybe for most of you, or at least the younger ones, cloud computing is what else, you might answer. 10, 15 years ago, cloud computing was in the research, not common things everybody used. And that's, I called it ubiquitous computing. The computing powers must be so efficient, so small, so cheap, that you can have easy access to the data, that you really can install it everywhere. And that's these 5 things you need that you can do Internet of Things. But maybe this was a little bit too academic now. Let's see what are the limitations of most IoT technologies. The first thing is, and I mentioned this before, is the small data rate. It has really a small data rate. If we are talking about the IoT system, typically we say 1 value a day. And value, I mean a temperature value, a water level of a river, for example. That's in many applications. 15-minute intervals, for example, in the power grid, that's another typical thing, but it's already a high data amount which is transmitted if you transmit a sensor value every 15 minutes. These small data rates actually are due to 2 facts. It's due to the energy constraint. We in electrical engineering call it duty cycle. Of course, maybe somebody would be interested to see the water level of Moldau every 10th of a second. But if I need to take a sensor value every 10th of a second, I need to spend energy to take it, to transmit it, and to maybe compute something inside. And if I do this every 10th of a second a day, I need much more energy than if I do it just once a day. So these small data rates are due to these energy concerns. And the second thing, which is also like the laws in quantum physics, is that if you have high data bandwidth for data transmission, you also need a lot of energy to transmit data. So the less you transmit, the better you are on the energy side here. So, and the other thing is for the network requirement is if you transmit a small amount of data, you usually can transmit it for a longer distance, which if you think about environmental monitoring, for example, it's much more easy to have one gateway station and cover 40 square kilometers, and this you only reach if you have a very low data rate. The second limitations and concerns in Internet of Things is privacy and security. We have such a cloud-based system where we have central entities where data is stored. Yeah? You need to be very careful about access to the data, who is allowed to really see the data. Maybe the river level of Moldau is of interest actually for everyone in case of a flood, for example, and will not really reveal any privacy issue. Yeah? But other data, if you have a sensor inside your home, I don't know if you want everybody to know that you turned on the heating now, that you watch television or whatever you do. Yeah? And beside these technical things in the data management and storage, also, in my opinion, it's my opinion, but I'm not the expert. Yeah, so that's something I'm aware that I'm here just as all of you, is that ethical and social implications need to be still investigated. At the moment, we are at the starting phase. We see cool technology. We can do this, and this. Yeah. There are, for example, social scientists working with children, and they already say that this surveillance, which parents possibly have with mobile phones, with Internet of Things, is changing the way how children are developing. Yeah? So that's things also to be considered. Yeah? Next limitations of IoT systems today is the limited interoperability and compatibility. It's that every device has its own IP address doesn't mean that every device can talk to every device. And usually these IoT systems, especially at the lower level, so at the sensor and the connectivity layer, yeah, they are really restricted to itself. You hardly can combine two of these systems. Complexity and scaling will become an issue. It's at the moment the cloud is strong enough, but if you do more calculations, many people and scientists think that will become a big issue. Yeah. Coverage and reliability, that's a big issue. In Austria, 2 years ago, they deployed, I think it was a LoRa network and the Sigfox network to cover whole of Austria, whole under parentheses. Many areas are still not covered. Then also Sigfox got bankrupt, so this network vanished from one day to the other. So coverage and reliability will be a thing. And the last thing, which is a limitation, is that the systems are very, very simple. As I said before, at the moment it's to take a sensor data and bring it to the cloud. No communication between sensors, between devices, no big data aggregation, for example. So this is also an important thing and a limitation. I talked before and I forgot that I have this slide here, so I'm a little bit surprised now, but let's think what I wanted to say here. Yes, range versus data rate. I listed here the most common protocols used in IoT systems. Yeah? And what you see here on the x-axis is the range. So if I put a sender here, a gateway here, then this range means the radius around where I can place my sensor systems. Yeah? And let's start with this protocol here, these protocols, the three ones. Yeah? these are really classical IoT protocols designed to acquire sensor data. And what they have is they have a really high range. So this is meters, 1 kilometer, 10 kilometer, or tens of kilometers. LoRa, for example, under good conditions can reach up to 50 kilometers of radius to cover a really huge area. But due to this electrotechnical laws of physics, the problem is that if I want to have low energy, I need to go to low bandwidth to make a robust communication. It's if you're in a noisy environment, to take us humans as an example, yeah, and you speak very clearly and very slowly, then there's a lot of sound information for a single letter, and your opposite is able to understand it very simply. If you speak like, so I missed the English term. If you speak extremely fast, yeah, then you have only a little bit sound information, and it might be hard in a noisy environment for your opposite to the receiver to understand it. And in this very simple words, it's similar on the electrical side. Yeah, so this LoRa has very broad signals, electrical, and therefore can very well be discovered also in noisy environments. But what else do we have here? Yeah, the second big protocol is Zigbee, which is more for the close range. It's just 100 meters, but therefore it's able already to transmit more data. But you still see it's in the kilobit range. Yeah? And then WLAN Wi-Fi, WLAN Wi-Fi. That's the classic thing, and it's the classic thing because it's so cheap and it's always away or almost everywhere available. Yeah. So here you have a different range to bandwidth area. Yeah. To use it, and actually it's too much bandwidth for most IoT applications. And here on top you have the mobile network protocols, and here some interesting thing is which. Rarely people know about 5G, yeah, is that in opposite to 2G, 3G, and 4G, which have a wide coverage, the 5G protocol has different coverage ranges depending on the amount of data you want to transmit. So if you're in the gigabit domain, even 5G, a mobile communication technology, will be just in the range of 10 to 100 of meters to connect. Yeah. So this is also important to know. But maybe this goes now a little bit more to electrotechnical details. I don't want to bore you with that. Spider diagrams, I also love them. Therefore, they're in every of my presentations. I will not read you now all the exact values. But here, on the side, you see the different properties of IoT technology, yeah, like battery life, power consumption, latency, how long it takes until your message is at the receiver, coverage, range, scalability. And the important thing you should remember just this picture is that you don't get everything, yeah? So, for example, if you want to have a high data rate, your battery life is low. If you want for the latencies, it's a bad thing, but for the coverage, if you want to have high coverage, then you might have scalability and range problems. Yeah? So you don't, unfortunately, get everything. Good. You can read it at the moment, and I'm already behind my time schedule. There are many applications. Yeah. So you can read it. I think I also have as a contribution to your faculty. No, that was a joke. Smart farming. That's a really important thing of IoT, or a development area of IoT things. So this part here is more really application side. This part here and maybe we'll go one by one here. This is the service offered by IoT systems. So you can use it for monitoring and supervision, which is data acquisition. Also, people who are doing data acquisition always say they are qualitatively more better than somebody who is monitoring. In principle, you get data and store it. Tracking is an important application. You want to know where your asset is. Remote control, security, safety, and analytics. That's the 7 services typically included into IoT applications. I talked at the moment about IoT, and IoT comes, and this needs to be clearly pronounced, from the consumer area. Companies first deploying IoT technologies aimed from the quality. Quality is not bad, yeah, but it's something like a television. If a television fails, you are annoyed. You might not buy it again, but you're not harmed if your television fails. Maybe the worst thing is that your kids complain and will get on your nerves, yeah? But it's not vital. But then industry discovered around 20 years ago, if we design industrial protocols in parallel to the consumer protocols, this will cost a lot of money. And look, these consumer protocols are so cheap because they are producing so many pieces. Yeah. Then they said, "Oh, Internet of Things is also cool for us, but we need the better Internet of Things." They called it Industrial Internet of Things, and they said, what do we need? And at least they pretend to have it. They want to have real-time applications. Yeah? They want to have data within short time, not every 15 minutes, every day one. And I don't know, do I get it in 10 seconds or maybe it shows up on my display in 20 seconds, which is in the consumer world. Who cares? If the SMS on my mobile phone is coming 5 seconds later, I will not miss my friend, still will be able to communicate with him. If I want to do motor control and get my control signal instead in 1 second in maybe 15, 20 or 10 seconds, then my motor control will not work. Yeah? So that's real time, which is seconds, yeah, instead of minutes and hours. Usually why I'm stressing this is that for industrial people, often real time is below 500 milliseconds. Yeah? We need to have real uptime requirements, so the systems must not fail. Yeah? It should be very reliable, have high precision, and compared to these consumer IoT systems, they need to make more data. Large doesn't mean gigabytes. Large means instead of 1 value a day, it maybe means 36,000 values a day. Yeah? So still really, really small. Yeah? And the application also, it's called Industrial Internet, goes much beyond what is industry. Yeah? It's the manufacturing, of course, but it's smart farming, agriculture, supervision of smart grids, and so on. Even health applications. Good. So I'm finished with my first block. Now I want to relax. You have to work. So I will try if I can use this magic whiteboards here. I would be interested, and I'm really interested about this. Where are you using such IoT systems or embedded systems? Where did you notice them? Maybe during your studies. Maybe you're not using it because you're just studying, but where did you heard about it? So don't be shy, speak up. I cannot believe, no.
For example, in my smartwatch, they are keeping track of my health care.
Okay.
So it always tells me my BPM,
Okay.
my heart rate.
Yeah.
So it's connected to my phone, which means it's connected to my to internet, and it's keeping track of my health.
Cool. Both cool applications, and cool that you're the first one. So it's much easier for the second one.
Smart homes. Smart homes.
Smart homes. Okay. Yeah. Have you heard in your studies, so now all professors, PhDs and so on, they are excluded? I hope that there are some non-PhDs here. Yes?
Self-driving cars.
Okay, yeah. What are you studying?
Technology and cybernetics.
Okay. Okay. Something else?
Automatic heating systems.
Okay. You have it connected to your smartphone or?
With my wife's smartphone.
Okay. Okay. Good.
Computer vision. Computer vision used by sensors and cameras to process images
Okay.
for AI applications.
Very good point. We will touch it in the second part of the lecture. On the one hand, computer vision is not classical IoT. Yeah? Computer vision, you can do it on your laptop, wherever you want, and it's not the origin of IoT. Yeah? Yet, optical sensors are a very important part, and you often want to connect them like IoT. And here you have these huge processing powers to interpret the image, and the small information, maybe for the tolling system on the highway, you want to have the license plate number of the car to charge him the fees of the highway. Yeah? No, not interested in the whole picture of the car. So very small information together here. So this will be an important aspect if integrated in IoT systems, and we will come to this. It's called the edge. Okay? One more.
Server monitoring. Sensors for server monitoring.
Ah, okay. Okay. One from this block here. Second row from the beginning. Any more here? Okay, self-driving cars. I make alright, the Google. Yeah, okay, good. Perfect. The middle block, last two rows. I mean, yeah, I'm trained by students over a decade or more even, so. Any idea?
Intrusion and security alarms.
Okay, I excluded professors and the first row. Okay, good. From this block, some more.
CNC machining and 3D printing.
I put it here, not in brackets. It's a little bit like the computer vision. Yeah, it's usually at these machines you have big networks already, so you don't really need IoT. But if you replace, for example, CNC machining by sensors in a big oil factory, which is spread over, I don't know, 5 square kilometers, then you will be in IoT because the sensors will be so far away that you need this technology. Yeah, thank you very much. Good. in this way, Hamza, please help me. We didn't do it perfectly, but I think we will make a short break of 5 to 10 minutes and then continue.
Okay, great.
Yeah?
We can do it.
I can continue to talk.
Depends on you. It is your...
Okay, we make 5 minutes break, the bio break for all necessities which might come up. So please be back at 11, then we start with the second part. Right, 11?
Okay, I think. Are you satisfied with the review?
They are not disturbing. And
If you look on the left side, you get in the middle line, so the voice by students in the past.
standing or is
The sitting.
okay?
Sitting. I am Michal. Stepan.
I need to see them a little bit more often to remember.
Never mind. When you will see him second or the third time, you will remember. to make it to get a photo together. So can we go out?
Okay, let's continue. Good. Let's see how to make our embedded systems, our sensors, smarter. And actually, that's what embedded intelligence is about. Those of you who expected now there will be a big AI lecture coming, if you want to have it, I will be happy to come in half a year. Then I will bring an AI lecture. But it's a part of embedded intelligence, but it's not the only thing. And I want to try to give you an overview of what is embedded intelligence. Embedded intelligence, if you want to define it, includes many things. Yeah. So, of course, it includes artificial intelligence. Yeah. But it includes artificial intelligence in embedded systems. So it's not about deep learning, about what Google is doing. It's about more trivial things. I have 10 sensor values from the past. I want to distinguish whether the new sensor value is an outlier, is an error. I want to predict whether in 15 minutes the sun is still shining and my photovoltaic power plant delivers energy. That's embedded systems, embedded artificial intelligence. It's also a lot about software services, machine-to-machine communication, sensor fusion, and optimization of hardware. And this figure here is from the Artemis, that's an industry association. They try to define what industry needs to create something which is embedded intelligence. And they did have mainly 3 layers defined here. And on the bottom, there have been the hardware guys, which looked up to the software cloud and said, how can we reach it and what do we have to do down at the earth? And on top, that's more or less the software people, so the ones looking down from the cloud and saying, oh gosh, down on earth, I don't know how to do all the calculations. And then they defined 3 layers they need to make this embedded intelligence true. They said the first thing is they needed something they called connected products. So what do they have to change in the hardware to make this vision of an intelligent sensor device true? They said a lot of things. They need new processes to be more energy efficient, make more energy efficient chips. They defined a lot of sensors which are really needed. Yeah? And read it. They say microphones is one important thing. Accelerometers, flow sensors, gas sensors, temperature sensors. That's not something new. But they identified these are the sensors which are most often used in the application. Yeah. They also said that they need to do a lot of energy efficiency in the packaging of the chips. Then they identified that LIDAR, micromechanical electrical systems are important things. But in the end, all they need to do is to change the design and architecture of the products to be able to communicate, to do computation, and to be really highly energy efficient. Then the next thing, what is identified that embedded intelligence will work is something which is called edge control. Yeah? They identified that the small sensor might not be able to do everything, that it needs something in between the cloud in the sky and the earth down where the grass is growing. Yeah? So at this point, the main research or necessities identified by industry is the edge AI. I don't like AI actually, I prefer the term machine learning. Yeah? Both locally and distributed, that's a big topic. Yeah? Then speech and image recognition, it was already also where you got in touch. This image recognition was an important topic. Sensor fusion and also robotics. I found my own errors. Perfect. So 1 point for me. Also robotics will play an important role. And then they look to this analytics and service layer. You remember the IoT system architecture I presented you in the last hour. So on this analytics and services, they identified we need reliable IoT service platforms we don't want to have these silos. We need one platform where we don't have to care to implement all the details that the magic happens. Yeah? It's, of course, they also identified AI will not only be down to the hardware, it will be on the top. So there is more deep learning here. Yeah. And the last thing I want to mention here is the APIs. They want to have APIs well-defined and interoperable. That the users can take device from vendor A, put it in the system. If the API is supported, it should work. If they can take it from vendor B, same API, and it will work. That's for industry a very important thing. Important due to two facts. First one, if you have a competitor, then a market exists, and the company hopes to get the best price. And the second thing, and that's even more important for industry, to have a backup. What happens if your supplier goes bankrupt, stops producing the product? Yeah? Then as an industry, and typically industries thinks in terms of 30 years. So many industries are built and then need to operate for 20 to 30 years before they are decommissioned. Yeah? During this period, it might really be important to have a second supplier if your first one fails. Yeah? And the middle thing, you can read it here, or maybe you have read it. That's more this application part, which at the moment for me is uninteresting, because today we will focus on that and certain aspects of this one here. Good. Look here, remember, connected products, edge products, analytics and services. That's actually what we called before an integrated sensor systems. Yeah? We have to work on the hardware to make the better sensors. On the electronics, that's this connected product layer. We have to make the software, that's the embedded AI and the edge control, and we need to have communication. So, I will go now through these layers, and by the research we have done at our department, try to introduce you a little bit. No, keep it, I will switch. Thank you very much. We'll switch to different sectors. Computer vision. One important subpart of computer vision is not in the visible spectrum of the light, but is in the infrared, so in the thermal part of the light. Yeah? And you have here what is called a microbolometer. I put this slide more that you have an idea what I'm talking on the next slide. A microbolometer is nothing like a floating electrical conductible plate, which is raised above the ground here. When a radiation comes here to this small plate, it's a pixel you can think of, yeah. Then there will be a current induced between the two contacts here and here. And if you look at more closely, yeah, then you have multiple of these plates or pixels in a raster, and you have your thermal camera or your infrared sensor. So that's how it works. You don't have to remember all the other details. Okay, I'm surprised again about my own presentation. Seems that I forgot to activate the next slide, but I can explain it on that. Yeah? So what is an important part of this connected products and the hardware which is developed there is the design here of this plate. Yeah. Typically, it's a flat plate like here, and now the next slide is missing, which shows a nice picture about this. By doing nanostructuring of this surface, you can make it sensitive to particular wavelengths. Yeah? And this nanostructuring, for example, is one of these chip technologies I mentioned on the overview picture. And for example, we did this to increase the efficiency and the spectral sensitivity of this sensor. So that's what you can imagine about connected products. Yeah. Connected products are mostly optimizing hardware, inventing new chip technologies. Optimizing hardware, here another example from us. We did an infrared pedestrian sensor, which is at a traffic light and should detect whether a pedestrian is coming, and if the pedestrian is here, the pedestrian should get green light very soon. If no pedestrian is here, the green light is actually not needed, yeah, and the cars have green light all the time. So what we optimized here is we make a really, really small PCB, an optimized PCB, which was just for the data gathering. So it was more or less here this infrared chips, that's the lens, and behind is this microbolometer chip, and we integrated it in a very special housing which allowed easy mounting. Yeah? So here the optimization was on the one hand on costs and on the energy efficiency. So the architecture doesn't stop on the connected product, so you also have to design the system behind. That is also this example of the pedestrian sensor, where we here included, again, in a very small form factor, a system which is then able to do all the image processing on a local way and just pass the information. Is a pedestrian there? Is no pedestrian there? Because that's all what the traffic light system needs to know. So we are approaching more to the software part. The question for us in this project was how to detect a human. I look here, I can easily count 1, 2, 3, 4. I discover the person's hide it behind another person, maybe putting down the head for rest to make the brain more active to listen. But for a computer, it's images like this. High resolution, 160 by 80 pixels. Half of the resolution, the sensor we used. Yeah? So, still, we can discover this most likely is a human. For a machine, this is a very, very big problem. How do we approach it? We approach it by something where we decided that's too much for the sensor, that's too much for this eye to interpret this picture. And here, edge control is coming in. And edge control, according to the Artemis Association, is this additional level which is able to perform speech and image recognition and other embedded AI algorithms which are not possibly be done at the sensor itself. So, what is, again, a definition? I personally love definitions, and I don't love them too. I want to invent systems and do cool things, but then when I write papers, all the reviews says give definitions. So, what is edge control? Yeah. So, edge control is a piece of hardware. So, it's a device that controls the data flow between a cyber-physical system, maybe an IoT device, and the network. And it has certain properties. It serves as a network entry. It does processing, monitoring, filtering, and translation, and computing and storage of data. Yeah? So, all what the sensor itself cannot do, the edge does. Yeah? So, the question about this edge is that it's not on the mobile device, so it's not on this cyber-physical system, but it's close to it. And what advantages does having been close? To be close, your advantage is you don't need a long range communication, so you can efficiently transmit high volumes of data. So this pixel image of our camera sensor. The sensor will be just for gathering the data, take the picture, quickly transmit it to the edge, which is still located at the crossing of the roads where our traffic light is. And then the edge is performing the necessary communication. If you are doing robotics, or it's robotics, I don't want to use drones. If you're using robotics, then on the robot arm itself, you are limited. You don't want to load big computers there. So you put very small cameras, very small sensors. And then you transmit all this data to the control of the robot, which is close to the robot, but actually detached from the arm. So this is one of the edge applications. So what are the drivers, or when am I introducing such an intermediate edge device? If I want to add storage, computer powering, and software very close to the user. When I have to process large data, if I don't know, maybe a lot of you have been on vacation in the mountains, and you know that there's often cows and other animals, and they might be supervised by a camera, but usually you don't have good mobile connection there, so it's impossible to transmit the image of the camera to supervise the cows. So you process large data locally in a way that you supervise your cows all the time. Maybe your image recognition is counting them if some is missing, and you only transmit small data over the mobile connection, so it doesn't matter. Maybe you have a different protocol, you have LoRaWAN to connect this. So here, if you process large data volumes, you reduce your data for transmission and gain, therefore, an important thing in the Internet of Things, that you only can transmit a small amount of data. You can also introduce the edge if you want to have autonomy and redundancy. Again, we are in the mountains with our cows. Maybe mobile communication is only working at certain times of the day under certain weather conditions. You want to supervise your cows, and if one cow is missing, maybe you give less food because one is said, oh, I will stay outside and eat the grass, it's much better. But whatever you're doing, supervising your cows and feeding, it's not the same. But I hope you can imagine that you can gain autonomy. The bad thing about my example was that if you want to supervise it remotely, nobody will be there benefiting from this redundancy. It could be for privacy application. One of my colleagues, most likely you will never get to know him, decided to over-automate his home, and he once had a break of a water pipe. And he said, boy, they had huge damage, it was really nasty. And then he said, I need a camera in all of my rooms to be able to see if there is something unusual going on. He even have a camera on his toilet. I don't want to comment this, but it's a privacy issue, and he included the edge device, so the toilet is supervised on its own, and there's only one alarm signal going out, and the camera is not accessible remotely via the internet. Okay, good. And these applications here are the ones where edge devices are most often deployed. It's with enhanced reality and wearable systems. That's one, because especially wearable systems have so little power available that they hardly can do any calculation except taking the sensor networks. We have it here, self-driving cars, including the Google car. So that's drone operation and automatic driving is also one of the important edge application areas. Public safety, that's the traffic lights, for example. Voice control, an example from airports where they supervise the background noise, and it's very funny that if there are some incident situations, the noise level change in a unique way over, let's say, at least in the Western Hemisphere, it's panic and something can be detected by the background noise. Also a very important thing, don't believe it or not, is that your DSL routers at home, they are identified by the internet providers as a very sweet spot to place services they sell to you. So you pay the energy for that. Often they gave you the device for free, but sometimes you even pay the device, and then they run their services on the resources you pay. 5G communication, I cannot tell you why this is so particular edge interesting. In every literature people say 5G, but I don't found a good example there. And robotics, I already mentioned them before. Good. Remember, we have these three pictures here. The interpretation of that is done by some AI algorithms. So you have really high computational power, and you need very low latency, because if I receive the answer that there is a pedestrian in front of the traffic light in 10 seconds, most likely this person will already have passed the street if there's no car close by. Especially younger students tend to optimize this crossing. So how did we do this? We used an AI algorithm which is called history of oriented gradient, which interprets the different pixels in a way that it tries to, for each of these areas, identify where most, let's say, very simple way explain the gradient, so where the main direction of this area is going, and this is visualized here by such star diagrams, but it's really complicated to understand. And since this project is 5 years ago, I don't remember. We digged into this algorithm and it was really, really hard to do. But in the end, the important thing is that for each of these sectors, I have to calculate the gradient, and then the pattern of this gradient is used by a support vector machine, which is not a neural network, but for those who don't know support vector machines, you could, in your imagination, say it's similar to a neural network. And then you discover here the different patterns, and then you have certain patterns which are humans and certain patterns which are not humans. And I hope that all these pictures are right. When the most important thing for this recognition is the head-shoulder section. And here you always in these sections see such a blurry fat star, which is here similar, here similar, here similar. Even if a person is on his knees or squatting, then you have also this real good identifier. Yeah? So that's just to explain the pictures a little bit, which is not important. The important thing for the edge is that this is computationally really, really intensive, because if you have a picture of a scene in front of your traffic light, there will be one person, two persons. There might be the person standing on the left, more on the right, and this algorithms then will, in an iterative way, make such arrays to interpret and have to repeat the calculation. So you need fast, energy-intensive computing, which you cannot do on the sensor. You can also use this for different object, so you can use this for cars, for example. And then there is no optical explanation to you what you see on the pictures. This is the infrared picture here. This is the highway. And this is the cars which are identified. So in this picture, it's quite good. So it identifies 4 cars already. Also, this picture identified this is on trucks. Yeah. So you have 1 truck here, 1 truck here. This is, I don't know, I would call it a false positive because this is not a truck, but the system identifies it as a truck. But from this small infrared data, I don't blame the system really big that this is, how do you want to distinguish between a truck and a car? Yeah. But here, that's the, let's say for me, general a problem about AI, that these are black box systems based on statistical data, so you hardly can explain in a logical way why the system identifies a truck here and a truck here. Good. So, another thing that you have a little bit of an imagination how we use this pedestrian sensor we developed. It's a crossing. We had 4 pedestrian traffic lights here, and we installed the sensors here on a real street, and it works really fine. The important thing was to have the availability. So if network connection breaks down, pedestrians are still recognized. We reduced the backhaul traffic, which was primarily from the users a privacy point. The mayor of the town where we installed it, he almost didn't allow us to install it because there was a camera. And if a mayor hears camera, he sees a riot already running to his office. So he was very pleased that there was this information that the camera picture is processed fully locally. Okay. So, good. I fear this is a little bit of a repetition. Again, you have the prime factors here on the left side. We had already some of them. Yeah. Why you use edge control? So if you want to increase your CPU power and storage, and you cannot do it on the sensor, you do it on the edge. Yeah? If you want to reduce the backhaul traffic, do it on the edge. And this has then on certain system properties, and they are here on the right, the effects, a reduced backhaul traffic will result in less uploaded data. Your loss of service will be reduced if you increase availability. Seems now very simple, yeah? Therefore I will not read all the others. Yeah? But this is for the application extremely important that you can have this. Yeah? So, for example, let's take one last example on the CPU power and storage. Yeah? At the moment we say the sensor cannot do it. Then somebody of my students said, oh, then I buy a new sensor which can do it. It's use a 10-year-old sensor for that. Of course, this sensor doesn't have the computer power. I have to say, yes, you're right. But then I told him the story that in the factory where we have been in contact, they have 5,000 of these sensors. Exchanging one sensor would cost 1 hour of labor, plus the costs of 1,000 sensors, plus the lost revenues due to the downtime. So for the factory, it was extremely important not to change the sensors. For them, it was an ideal solution to introduce an edge which interprets the sensors and establish the connectivity and data processing. Good. Guess what this picture is? Somebody with eagle-like eyes will have the possibility to read the caption, maybe giving a hint, but I will solve this puzzle. This is the Google Edge data centers worldwide. So each of this yellow dot here is what Google calls the edge. For Google, the edge is a data center. That's what they have 15 data centers. That's really huge. That's the thing where you might have read in the news recently that they build own atomic power plants or want to restart an atomic power plant just to operate the data center. Then they have something they call edge points, which they have 100 times worldwide, which are still huge data centers. And then they have edge nodes, which you can think of that the Google edge nodes are typically two 19-inch racks that high stuffed with blade servers. And these are these dots. What do I want to say by that? Is that the edge also depends on your application area. For the traffic light system, for example, the edge was it was installed in the box where all the power supply and everything for the traffic light is installed. So it was on a cabinet on the roadside. For the robotics example and some augmented reality, maybe the edge is your DSL router where the software runs, which offers the augmented reality for ambient assisted living in your home. So there are many things where it can be installed. Typically places, however, are all kind of base stations. So that's this connectivity layer or gateway layer of the IoT architecture. All kinds of routers, they're a little bit different, but in the end, seen from a very high level, the same. And that's an important trend, is that they are virtualized and therefore can almost run everywhere where you have something which is similar to a computer. So, nevertheless, depending on the service provider, the two main things from how it's installed, is that you always have a low latency wireless channel to this edge. That's really important. So for example, on the DSL router, you have WLAN, you have low latency, high bandwidth on that, to connect your dumb edge devices. And you have, in particular, additional this local computing power there. Good. So, what are you doing on the edge? So, logically, most IoT technologies are star-like topologies. They don't allow peer-to-peer communication. There are rare exceptions, but as soon as they are in peer-to-peer communication mode, they often lose some of their properties. Zigbee, for example, can be run fully meshed, but then it will suffer drawbacks in efficiency. So in most IoT systems, and I signed it for the last years, I can sign it right now, at the moment are really star-like. You have hundreds of sensors, they report to one gateway or to 2 or 3 gateways, and then in the cloud to your applications. So what do you need to do here? And that's more or less these 4 things, which is important to either do on the edge or, if you like, also in the cloud. But in the cloud, you reduce the latency. Increase the latency. So it takes longer until it's performed and until the result is available. So the first thing, and you need to clearly distinguish between that, is that data aggregation is simply collecting information, applying very simple mathematical operations to generate new sensor values. What is typical data aggregation? Think about the power grid, for example, In each household you have an electricity meter, and if you want to know how much energy is consumed in a whole town, you add up all the household meters and get the consumption of the town. Again, very simple, but data aggregation is simple. Yeah. Beyond data aggregation is sensor fusion. And how does sensor fusion distinguish from aggregation? Yeah? You have two things to distinguish. The first thing is you can take sensor values of different type. So you can combine a humidity value and a temperature value to compensate, for example, for the temperature error in the humidity. That's a very specific thing about humidity sensors. They have a huge dependency on temperature. So the temperature changes by 3 degrees and humidity stays the same. Typically the sensor value also significantly changes. So first thing, combine sensors of different types. And the second thing, and that's also different, you combine it, even if you combine the same values in such a way that you aim to increase the quality. Yeah. The third thing Edge is doing with the data, it's substituting of missing or wrong values. That's also an important functionality. Might be very simple, repeat the last value, might be extremely complicated, use a neural network to predict what this value might have been. Yeah? And the first thing is, is a health state detection, so that you know whether your sensor devices are still operating properly. Can be done very simple by a way that you say that you have, if your sensor value is above a threshold, it's most likely erroneous. It could be counting outliers, whatever you want to do. Yeah? Important thing with data aggregation, bracket, but with these things, remember or consider that this is data modification, so that you might introduce also wrong data into your system. Good. We finished the next layer, the edge control. Let's go to the topmost level, the most software side level, the analytics and service layer defined for the embedded intelligence. It's, as you, for sure you remember, about these multi-IoT service platforms, AI and APIs. AI, I will not touch. APIs, also not. I will go to these service platforms. The concept of digital twin is that you want to map a real world object, in this case this nice plant here, into the digital world to make it accessible. So here a very nice sensor supervising the humidity in the soil, the temperature here, is transmitting data to the digital twin. The digital twin, it stores this data, so that you have here the sensor data, humidity, time. Maybe you also have a GPS coordinate if you're living in an area where plants tend to move or stall. And you have a lot of other things here, including a better growth service, which reminds you that the humidity is too low, and which gives you maybe some advertisement, go to the shop and buy some nutritions for your plant, whatever. And then the second thing is that this digital twin is just a representation. So it's connecting them to an app, for example, on your mobile phone, which does certain things with the data. So I think I need to be a little bit maybe more clear on that. What is the specific thing here? And I will come to that. Is that the app, so the user, do not directly access the plant. It will be impossible if on this small battery-driven sensor you are asking every 5 minutes, is my plant okay? Your mother is asking maybe every day because she is experienced saying, is it Did you water your plant? Yeah. So this is the important thing here. But we will go into more detail. So, as I said, again, it's my favor on definitions or unfavor, is that the digital twin mirrors a physical object, device, asset, whatever, in the best possible way. So, it's this IT representation. It's the only one to send data and to receive data from the actual physical object. And it's in a way, you can call it a single truth or a single source of truth about your object. So you introduce your object by a digital twin into the IT world. Yeah. There are other definitions. I will not read it in detail. You can do this while I'm explaining. Yeah. Other definitions include more extended properties. They say a digital twin models the system, which means it's not only the only source for sensor values, but it describes how your system works. So what happens if the humidity is too low for your plant? It will die after a few days. Yeah? The data flow is also here in this direction, and you can have additional functionality. Yeah? So you can have algorithms stored there, like a watering concept to make your plants blossoming very soon, for example. For orchids, this is very important to put it in the right temperature and give them the right amount of water to make the blossoms stay very long, for example. So, even more of an extension. Yeah? So we have this concept from before. We have the communication with the device. We have the storage. We have the algorithms. And this might now seem to be very redundant for you. And in a way, yes, it is redundant. But it also has certain differences. Yeah? It's in this definition here. You, for example, see that in a literature review I did, the storing of the history of the state, so of the humidity, how humid was your soil yesterday, for example. That's for many applications and for also then IoT platforms, not a mandatory aspect. Yeah? But you have again the sending and receiving. You have, and that's a property all digital twins compulsory must do. They must store the current value. They are optional. They can store the history of it, and you have also the important point of the user interface. I have to look a little bit on the time. Yeah. Another, here's the digital twin. I'm going here. Now I'm looking from the other side, so I move here. So you can distinguish between three types of digital twins. Yeah? The first and simplest type is just a data container. Yeah? So it contains actual states. It contains, for example, manuals, properties. That was actually how digital twins began in industrial automation. Yeah? This was a pure concept for maintenance and actually just to store the manuals and the protocols of the maintenance of the devices. Yeah? So you had a robot, and the digital twin had the manual so that the engineer maintaining the robot can easily type in the number of the robots, then he will get displayed on his computer the manual, what he has to do for maintenance, and then he wrote his maintenance results. Then the second type of digital twins is the functional representation, yeah, which includes the control of states. So you can switch off the robot. So you can tell the digital twin, look, in 5 hours there will be maintenance. Shut down the robot before the worker is there to maintain it. Yeah? So that's this functional representation, which can be really, where is it? it's not working, battery empty, which can really be big services, including model and prediction of the behavior. And the third type of digital twin, which you can identify, is that the physical asset connected to the digital twin doesn't even exist. Yeah? So it's a simulated object. That's especially important for planning and change management. So imagine you have a factory, you have 30 robots, and you want to add a 31st robot to your factory. Then you can take the digital twins into your simulator, which gives you the real data or what is really happening in the factory, and virtually adding a certain robot. And this twin will behave like a robot, although he is not connected to an actual robot. You can check in your IT environment how your factory behaves. So if there's, for example, some problems in communication, and therefore do it much more easy. Good. So now I have to hurry up, and I think I will need to really go by this section quickly. It's the last one, by the way. I will see what I tell you here. Yeah. I think I will only take you on a journey on this picture. Yeah. It's the DITO digital twin platform. And what you see here is, again, the main functionalities. Yeah? You have your devices here. Yeah? And typically each of these digital twin platforms, and here in a very simplified way, contains translators for the different communication protocols. In this case, it's MQTT. So each device is via a bridge or another stack, inserting it via a broker into the digital twin platform. In the digital twin platform, you have two main things here solved by InfluxDB and the MongoDB. It's a storage of the status. That's the InfluxDB time series, and the MongoDB is for more the configuration data. So that's the storage capability. And then the core of the platform is that it manages the access from the applications. Yeah? So again, resolving this discrepancy between how often can I connect a sensor, bandwidth limitations, energy limitations, versus the frequency requests are coming from the internet. So that's everything. And in this way, what at least my students also like, I'm finished 5 minutes earlier than planned. But we also had a shorter break than planned. In this way, thank you very much for your attention. If you have any questions you want to ask now, I can imagine, since this was a really quick strive through embedded intelligence you might have, then I'm really open for questions, and you're welcome to ask them. So thank you very much.
I'm curious about your pedestrian recalculation system, because it looks like the image resolution was in amount of kilopixels. Yeah.
Now I have to calculate. Our sensor had 80 by 45 pixels per one image, and we took I think 10 images per second.
Okay. And how you sorted out about the computation? Because if you are going to use the support vector machine and histogram or in
Yeah.
It doesn't need a lot of computation, so you prefer to do the computation at the site, or you transfer the data to the servers and
we did the computation at the site, so on the edge device. So we detached it from the sensor. So we connected 4 sensors. I think it's 4. 4 in principle. I think we would have been able even to connect 8 sensors, but we connected 4 sensors to this edge device. Yes, it's not extreme computation. So we have been able to do it on a Raspberry, which I would not choose again. I would choose it for easy development in the lab, but on site this Raspberry was the worst decision we took. Not because the Raspberry itself is bad, but it's simple things like the SD card failed all the time. And yeah, I see nodding here that there's similar experience here in at this university about this. So yes, it was not too much, but it was at this time a Raspberry 3, and it was fully loaded by interpreting these 4 sensors. And this is, not little. It's, I would say, still already high computation. Does this answer your question? Okay. Good. Any more questions? I think I will stay at least 5 to 10 minutes more here. So,
But maybe one.
Yeah.
So do you think that AI is a part of our life, and do you think that we'll be still more and more dependent on AI in the 5 or 10 years? Or will we still be people like we are?
it's almost like the question somebody asked me, is the radiation of mobile communication dangerous or not? It's very hard to answer. I think that AI will increase. It's 5 years ago it was in 1 out of 10 projects of us. Now it's in, we hardly have any projects where there isn't any AI. I think that we will have to learn how to use AI. That's, let's say, we all use Google Translate, DeepL, whatever, but we now discover that it's not really that what we promised. I think what is the research, at least from my side, from the sensor side, we have to much more research on the reliability. So how to handle false positives and false negatives. And we need to go into explainability. We need to go, It's typically AI cannot be explained because it's a purely statistical black box system. It's simple math. You calculate your weights according to the statistics, and the outcome is what it is. At the moment, what we are doing in our research, but the colleague is doing it, they are using AI for magnetic material design to reduce rare earth materials in magnets, to make them more environmentally friendly and cheaper. And they are working on cascaded systems which are introducing laws of physics into AI. And I think that this will be an important thing. So, a little bit exaggerated example, there have been a study of big AI failure where AI should identify a wolf in a picture of dogs and wolves. And in the end, it turned out that the AI identified the background, the white snow, because most wolf pictures have been taken in winter or in northern region where there was a white background. And I think if we could have given this AI a notion that the wolf is not the full extent of the picture, then it would have trained other differently and maybe give more reliable results. But this is a really open area of research.
Thank you.
Good. So for all who don't dare to ask it in the auditorium, I'm here for 5 or 10 minutes more. So come here to ask if you have something you don't dare to do now. And Hanzo, do you want to do some final words, or should I say the lecture is over, the buffet is open? Or
I think we would like to express you a great thanks for your lecture and your visit, and a small present for you, and enjoy it.
Thank you very much. Thank you.